Over the past few months, I've been experimenting with other amplifier circuits out of curiosity, using my sound system that I mentioned in a prior video since my Elm 386 project. What you see here is a portable device using the TDA7267 chip, designed for TV applications with efficiency adequate for battery power. Unsatisfied with my amplifier knowledge and the TDA7267's distortion, I learned to design my own audio amplifiers that produce less distortion due to their simplicity. Before I start the comparison, I need to go over the basics in a PowerPoint so it's easier for you to learn than it was for me. Let's begin. And now to jump directly into the presentation. So this is the common emitter amplifier, which is the basic amplifier schematic. Most amplifiers go by this schematic. So anyways, how this works is that you have a small audio signal which feeds into the base, and the base simply switches the power supply current directly proportional to the audio signal. And this produces an output signal with a higher voltage. Now, this is just a preamplifier and not an output stage or standalone amplifier because of the collector and emitter resistors. These take away power from your speakers if you want to drive them. So how do you mitigate this issue? Well, simply you get rid of the collector and emitter resistors and the bypass capacitor, since that's not needed. And this output capacitor is also irrelevant. The output terminals are right here, connected directly to the power supply and the collector of the transistor, so that the transistor can switch as much power as it can directly proportionally to the audio signal. So it all makes sense, and it's all simple, and it's all linear. And to maximize the current gain, you want to short the emitter directly to ground. So you're really just using 4 components and the speaker. You need the bias resistors so that you can set your transistor in the active stage so it can operate properly. And you need the input capacitor to protect the input audio source and to mitigate any DC interference against the audio signal. So yeah, my circuits will be following this more simplified model right here, and these can drive speakers directly, but I won't be doing that in this case. I will be using a more elaborate setup which is more faithful to the audio. Now, before I continue, there are some considerations like BJTs and MOSFETs. These are different types of transistors that can both be used in this schematic, but they have some differences. Like the BJT at its base needs both current and voltage, which can make it less efficient and more complicated. The MOSFET is more simple as it needs voltage at its base only, and it's more efficient because it's more linear and it has better frequency response, so it's more preferable in this setup, which is Class A architecture. Class A is not very efficient, but it is faithful to the audio and it's simple to learn, so we will be using that. Now, moving on to the amplifier load specifications, we have a passive crossover. This passive crossover is connected to a piezo tweeter, an 8 ohm 4-inch woofer, and a 4 ohm 10-inch subwoofer. So we're going to have pretty faithful audio from that. So you don't have to really use a crossover. You could use a single speaker of any type as long as it's low enough impedance, but the audio will not really be that faithful and your speaker could be at risk of damage. So there's that to consider. Moving on, this crossover is 3-way, meaning it filters for high, medium, and low frequencies to their respective speakers. Starting off with the low pass, we simply have an inductor to filter for the bass frequencies, because the inductor actually has passive qualities where if you feed a low frequency signal through it, it will be resisted by the inductor less than higher frequencies. So we exploit this property to filter for bass frequencies to feed into the subwoofer. Next up, in the mid-range speaker, we have a bandpass in front of it. And in this case, the bandpass combines the filtering properties of both the inductor and the capacitor. And a capacitor filters for higher frequencies, so it is inverse in filtering properties to the inductor. So if we combine these properties together, we have a window of filtering that allows for the medium frequencies. Last but not least, we have the high pass. Now the high pass is simpler and only needs a capacitor, which, like I've said prior, the capacitor filters for higher frequencies as it will resist AC less than DC. So yeah, we have faithful audio as a result of all of these mechanisms. And another thing to be considered is that half of the ports are used for simplicity's sake. The other ports have some other wiring that I'm not going to get into because they're just not important. And this setup is specifically more faithful to the audio because the mid-range speaker itself is at least coaxial, so it has even better frequency response. And as far as the specific components are concerned, I have the capacitors but not the inductors, unfortunately, because the inductors do not have their inductor values imprinted on them. So you'll just have to approximate the wire turns, the wire diameter, the core material, and the core diameter, because it's not easy to approximate and gauge the inductance of these standalone components. So yeah, this is the setup that will be used in the video. So before we go over the practical comparison of my amps, let's go over what I'm going to be comparing my amps to, which in this case is the TDA 7267, which is a Class AB amplifier rated at 2 watts, which is highly efficient, like at least 80%, and operates very well from a 9-volt battery, like any 9-volt battery for 1 hour, like full capacity, bass pumping for an hour just from a regular 9-volt battery. It's very formidable, and it even has a standby mode where it will not amplify the background noise if you're not playing any audio. So it is very smartly designed that way. And it will drive 4 to 8 ohm speakers, which gives you a wide variety of options. And I have used this IC in an augmented circuit where it has LED audio chasers, audio input attenuation, and also a switch to turn it on and off. So you have power control there. So basically, this is the benchmark for my amps in terms of performance in many aspects, including efficiency, audio quality, and etc. And I will give a spoiler that the audio quality of this is actually outmatched by at least a couple of my amps. So it'll be a very interesting competition.
What's up? Not much. Just hanging out. Hey, who's that guy over there? The camera pans over to reveal the 36th gem, standing awkwardly in the background.
So let's begin with the first amplifier of the list, which involves an IRFZ44N transistor. So this circuit delivers around 1 watts of power at most, which is similar to the LM386 in performance, which is rather poor. But this is good for demonstration purposes with its 4-component design, making it rather simple and easy to follow in terms of amplifier theory. And another trait that dooms this to be a demonstration circuit is its rather low efficiency of 12% at most. So the vast majority of the power used is simply converted to heat, which is not what we want. We want to convert as much of that power as possible into sound. And speaking of making sounds, the speakers in question need to be 4 ohms for optimal performance. And this circuit is rather unique in mechanism in the fact that its output stage differs from my other circuits. The source of this MOSFET is not connected to ground like in my other designs. It doesn't work this way. It only works if its drain is connected to the power source and its source is connected to the speaker. So it can still manipulate a sizable amount of current proportional to the audio signal, but not as much. And as a result, this circuit is rather low power, but that's fine. Like I said before, it is a model. And what you can learn from it is, of course, the transistor, the filter capacitor, which filters for mains AC, and as a result, the main 60 hertz noise is filtered out of the amplification, and we have cleaner sound coming through our amplifier without the power supply interrupting or just drowning out the noise that we want to listen to. So moving on, we have the bias resistor. And this is rather unique for this circuit because with my MOSFETs, at least in the amplifiers I use them in, they need 2 bias resistors for adequate operation in the active region. But this needs only 1 resistor with low resistance at that, which makes it really stand out in terms of MOSFET amplifiers. So yeah, not only is the bias resistor low resistance and not high resistance, but there's also only 1. So this is really something different. And last but not least, we have the input capacitor, which protects the audio source and mitigates DC interference on the input audio signal. So yes, this is the basic amplifier circuit in operation, and we will see it in practice shortly.
Hey, have you guys ever heard of the legendary Porcus the Clown? Oh, yes. Most terrifying clown in all the land. Wait, are you saying that Porcus is real? Yeah, I heard that he haunts the abandoned circus down the street. And he's not like any normal clown, he's got magical powers.
Next in series, we have an audio amplifier circuit that features a Darlington pair of dual 2 and 3055 bipolar junction transistors at the center of its operation. And this circuit outperforms the last one, starting with its power performance. It will supply a little over a watt of power to your speakers. and this is at the same efficiency as the last amplifier. So that's impressive. And how it works in its design is that this time this borrows from my theory of how I design my amplifiers, and it powers the speakers starting off directly with the power source. And the current inside the speakers is directly changed to the audio signal using the Darlington pair, as we see connected in series to ground. So this is the main path of the power. It flows through the speaker, the low resistance resistor, and the Darlington pair. Now, not all of the power will be consumed in the output stage, and some of it will actually be redirected to these LEDs, which will light up proportionally to the audio input signal. So as a result, we have audio chasing LEDs. So that's another cool feature of this circuit. And this circuit uses a Darlington pair because that makes the amplifier more efficient and sensitive, because you have a transistor driving another transistor. So it's like you're combining the power of the two transistors. And notice that this has the same resistor bias arrangement as the last audio amplifier. So it really testifies to the versatility of this resistor bias arrangement. Now, there are drawbacks to this circuit though, starting with the fact that it starts to have poorer performance as it starts to respond to the low ends of the bass frequencies. And what this sounds like is more muffled and quieter bass frequencies. So we don't want that. And another thing we do not want is more power supply noise, which is the case with BJT amplifiers. And this one is not exempt, and no matter how much filtering you can try with your capacitors connected directly to ground, still you will still have a little bit of mains noise left over that you can still audibly hear. And this is not the case for a lot of your MOSFET audio amplifiers. So that just goes to show of the differences between those transistors. So we will get to see all of this in practical performance coming up shortly.
Begin the recitation again. Cool the raven nevermore.
Be that word our sign of parting, bird or fiend, I shrieked upstarting. But soft, what light through yonder window breaks?
No, Jimbo, that's not even the right play.
Next in my amplifier series is a better BJT design rated at 2 watts. Although not listed, it is rated at 25% efficiency because it is producing 2 watts of audio out of 8 watts of power supply. That is 1 out of 4, and thus 25%. And this can drive 4 ohm loads like the other amplifiers, but unlike the amplifiers, it is rather prone to instability while idle. And I believe the reason why this is because it has 2 stages, a pre-amplifier stage and an output stage. And the reason why this is because Q1, or the BG243C in this case, is too insensitive to be driven by the raw audio signal alone. So you need a preamplifier. And how you do this is you get a smaller transistor like the BC546, for example, that has a high current gain. With this high current gain, it can be sensitive enough for the audio signal and supply a high enough proportional audio voltage at the base of Q1 so that it can drive the speaker with as much current as it is allowed to. So this is exactly how we have two stages providing audio amplification. Now this is not perfect after all because, like I said before, there's instability, and also another imperfection in this design is that, like BJT designs, it is rather prone to power supply noise. So even though the power supply noise filtering is better in this circuit, probably because of the transistors, it is still not as good as filtering power supply noise from MOSFET amplifiers. So you're still going to hear the power supply noise at least a little bit with all the capacitor filtering, but it is still adequate, at least to me. And how the preamplifier stage is done, to be specific so you don't mess anything up, is that you need equal resistors on each end of the collector and emitter of Q2 so that you have an equal swing of voltage so that you're amplifying the whole wave. And we're going to see all of this in action and in practice shortly.
No, man, that's a lot of people. You in or out? I mean, X'd. Mine McLeod's house later. Jim and Jimbo pull up in front of my mind's house. All right, let's do this.
Last in the amplifier series, I have a better MOSFET design this time, which is rated at 2 watts and is again 25% efficient energy-wise, which means that it is drawing 2 watts from 8 watts of power. So yeah, still pretty inefficient, like just as inefficient as the last amplifier, but still this has some upgrades. Like for one, it can accept higher voltage than 12 volts, meaning that you can actually go beyond 2 watts of audio and perhaps up into the 10-watt range if you would like. I mean, that can get pretty loud, and that can serve some even bigger applications if you want. And like the other amplifiers, it usually drives a 4 ohm load impedance. And the thing is with the power supply noise filtering for this design is that it's actually way better, and with 2 millifarads you can barely hear the power supply noise at the output. So that's a really good upside to this design, is that you can filter out the power supply noise with ease. Even with like 1 millifarad, you can do a considerable amount of filtering just with that capacitance alone. And another thing to note about this design is the wide frequency response. In fact, the high frequency range is especially notable compared to the other amplifiers and its better performance. And also, the bass from this amplifier is richer and smoother and louder. So overall, the wide frequency response is just a step up compared to the rest. Now there is some slight differences in this MOSFET amplifier compared to the last, in the fact that it is using a better quality MOSFET, an IRF 630, which is a high power MOSFET for switching high currents, like up into the 9 amp range. And also you need 2 high resistance bias resistors, because the gates of this MOSFET is very sensitive and we do not want a lot of current getting in the way of the audio source. So we need only a tiny bit of current flowing through here. So the audio source can just switch the transistor. So yeah, it's a simple working, and it's very versatile as well. I mean, it's at 2 watts, so it's decently loud. And I would say that this is my favorite amplifier of the bunch, and we will see why with practical examples in real life shortly.
Just deceive the public? Yeah, this doesn't feel right. Relax, it's just a harmless prank. X'd Town Square Day. Attention, everyone. We have something to tell you. We put a fake word in the dictionary, and we're sorry for deceiving you.
In summary, we dove into the world of amplifiers and explored a variety of circuit designs. I hope along the way that you have found this video informative and engaging. Throughout this comparison, I presented you with various amplifier options, ranging from homemade circuits to utilizing a specialized amplifier integrated circuit. As we witnessed, the amplifier IC has proven its superiority, offering exceptional performance in terms of power output, efficiency, and noise performance. However, my homemade Class A amplifier circuits are more faithful to the audio signal, but that is not very evident in the video, as you would need to observe the performance in person. But our exploration doesn't end here. In a future video, we will delve into even higher power amplifier circuits, allowing you to take your audio experience to even higher volumes. With this video instance, I give an electrical engineering contribution to the internet and make the journey to learning amplifiers that much easier. Thank you for watching. Leave a like, subscribe, and stay tuned for future projects.